logistics. Okay.
Oh, shoot, yeah, forgot to say.
My selfie post. All right. Let's get started. I'm still I'll just level with you. I'm still working.
I definitely ain't gonna level with you.
All right. I'm still working on grading the homework. The first two labs are graded. Lab 3, I should have, the labs and whatnot are fairly quick to grade, so I should have the labs graded by the time that we do our next lab. That's gonna, I think, gonna sort of be my goal with the labs, is that by the time you come back to the next lab, so like by the time, so this week we're gonna have lab 4. By the time you show up to lab 4, I'll have lab 3 graded, and so we'll work that. Homework 1, my goal is to have that graded by Wednesday. It's just, there's just a lot of problems and there's 35 people, so that'll take a little while, but we'll get it taken care of. Exam 1, okay? So we review for the exam on the 13th, which is Wednesday, okay? So what I'll say about that is the way that I do exam review, some of you have had me for class before, but for those of you that have not, okay? So the way that I do exam review is I come in and for about 5 or 10 minutes, I will discuss the exam logistics, the format of the exam, what's going to be covered on it, and just so everybody's aware, what the exam covers essentially is everything up through today's lecture, okay? So lectures 1 through 6, the first 2 homework assignments, I sort of say the stuff we've discussed in lab, although it's primarily intended to be a lecture exam, but the labs sort of align with what we're talking about in lectures. I mean, we're talking about leveling and we're doing leveling in the field. But we'll discuss that, and so my point is, on Wednesday, I'm going to come in and only talk for about, I'm only planning on talking for about 10 minutes or so. And then the rest of the time is you all asking questions. So if you've got questions about homework problems, if you've got questions about types of questions on the exam, concepts you didn't understand, what have you, that's what we're here to do, okay? So come prepared with questions on Wednesday. Now the following Monday, I'm not going to be here, so I've pre-recorded a lecture for that. And then we will celebrate next Wednesday. So not 2 days from now, 9 days from now. Okay? Does that make sense? Okay. All right. Today what we're going to do is we're going to continue our discussion of leveling. If you recall, what we were doing in class last time was an equal adjustment of error. And today what we're going to discuss is a weighted distribution of error. It's really not more difficult, but it's a little more involved, I would say. I sort of like this method better for a couple of reasons. Bless you. One of the reasons is I do think it adjusts your surveys in a more logical fashion. The other, there's 3 reasons I like it. One is that I think the adjustments have a little bit more of a logical basis to it. The second is that in order to do a weighted adjustment, you need to determine horizontal distances, but you need to determine those anyway in order to classify the survey as first order, second order, third order, etc. If you remember in the lab that we did on last week, I gave you the length of the survey. Now you're going to be able to determine that on your own. The third reason that I like a weighted measurement is that in order to do a weighted measurement, you have to read all 3 wires. And there's benefit to that. I don't want to get too far into the weeds, but there's a benefit that you all are going to see when you're taking your field measurements. This method sort of has a way of helping you ensure that the measurements that you're taking are correct. And we'll get to that here in a bit. I don't want to information overload you, okay? But let me talk about some field considerations. So again, I think we mentioned this in lab, but I did want to mention it in class, the idea of rocking the rod or waving the rod. The idea is that the lowest point on the rod is when the rod is perfectly vertical. So if you take the rod and you rock it back and forth towards the person sighting the rod, what happens is, so like if the rod's like this, okay, and you read point C, when you rotate that up, that's higher than the actual reading, which is at point B. Same thing with point D. If you read point D, if you read point D and rotate it up, that's higher than the point that you're wanting to read. So if you're rocking the rod, whoever's sighting the rod, they'll see the crosshair bounce up and down, and the lowest reading is the actual correct reading that they want to take. So if you're rocking it, it can help improve accuracy when you're rocking it, because whatever the lowest value is, that's the one that you want. Does that make sense? So that is a technique in the field. Another thing that I think you now kind of get what I'm talking about, I think this happened to a couple of groups in the field Wednesday and Thursday, is that whenever you're setting up, make sure you're not setting up like this to where when you shoot the instrument towards, you can't read the rod because the rod is too high, or flips are the other way around, is if you extend the rod all the way up and it's too low. I don't think this happened too often, but there were some instances where this happened near that hill between Buskirk and where that field is in front of Old Main. You know what I'm talking about? That big sort of ridge hill in front of Buskirk. I think that happened to a few of you. So yeah. I have decided that in lab this week, we're going to run the same loop that we did last week. But I was thinking about doing different points, but I think we're going to do the same ones, but we're going to do a weighted adjustment. So it's going to be the same loop. From a field perspective, the only thing you're going to have to do is read all three. So you'll see what I mean, and you'll see the advantages to that here in a bit. Okay, let's talk about this actual error adjustment. It's a little bit more involved, but I think you'll find there's some intrinsic benefit to this approach. Okay. Now let's go back to the differential leveling loop that we did. This is the one that we did in class. So if you remember in our previous lecture, we had one set of slides, one set of leveling data that was sort of in the slides, and then we had another one that we did by hand. This is the one that was in the slides. Now, this set of notes is a little different than the one that we had last time because there's some new data. When we collected data in the field last week, all we were really collecting were backsights and foresights. That was it, right? Now we're collecting something else. So for our backsight, not only do we have a backsight, but we've got these new terms here, this backsight distance. And over here, we've got foresight and foresight distances. Okay? Now what these are the distance between the instrument and the backsight, the instrument and the foresight. How do you think we determine that in the field? The upper and lower stadia, right? So we read the upper wire, we read the lower wire, and then how do we determine the distance? Anybody remember how you do that?
Difference times 100.
The difference times 100, right? Because our instrument is calibrated such that every unit of difference corresponds to a 1 to 100 scale. Y'all remember that? Mm-hmm. So what we can do is we can read all three wires and we can get the distance, right? Does that make sense? Okay, all right. So again, to check closure, it's the same way. We take the closure, we can say sum of the backsights minus the sum of the foresights, so we get negative 0.06. Or we can take the final elevation minus the initial elevation. But the other thing I want to add to this discussion is this. Okay, this right here is the length. Okay, now what do I mean by length? All I'm doing is I'm adding up this and this, this and this, this and this. I'm adding up all the yellow numbers. Okay. Now I propose that the sum of all those numbers, in which case this is 520. 520 is the total length of the survey. It's 520 feet, right? If you remember, we need a K quantity in order to classify the survey. Before, I was just giving it to you. How do you compute it in the field? Just add up your backsight and your foresight distances, right? Because think about this right here. So here's the height of the instrument. It's 75 feet to the backsight, and it's 75 feet to the foresight. So that's 150 feet between your benchmark and your first turning point, right? So you keep doing that, and you can compute the total distance from backsight all the way back to the backsight again. It's just some of these numbers and the sum of these numbers. So it makes that calculation a lot easier. With me so far? Okay. Now, how do we do a weighted distribution of error? Okay. Now, in an equal distribution of error, what we did is we took that closure and we said, okay, the closure is negative 0.06 and there's three setups. So we'll adjust each elevation by plus 0.02. Just take it and divide it by 3. We're not going to do that here. Instead, what we're going to do is we're going to adjust the elevations by a ratio of the total distance from benchmark 1 to the total distance for the entire survey, okay? And so what we're gonna do is we're gonna have a fraction that we're gonna compute for each setup, and then adjust that elevation accordingly. And so the final setup is gonna be the total horizontal distance on the bottom, but then on the top, it's gonna be the horizontal distance from benchmark 1, but that's also gonna be the total horizontal distance because that's gonna be the end of the survey. And so we'll go back to our initial benchmark. Let me kind of show you how that works. All right, so let's take a look at this, okay? Now, your field notes are gonna be set up a little differently. When you do this in the field, what you're gonna do is you're gonna have your back sights. When you record your horizontal distance, usually you're not gonna be able to record that distance directly. Instead, what I want you to do is I want you to record the upper and the lower stadia. You'll see why here in a bit. Again, I don't want to get too far into information overload, but you will here in a bit. When we do our example here in a second, you're going to see this like number slash a number here. Those are the upper and lower stadia. You'll see what I mean. Now let me show you how a weighted distribution of error works. Okay, so here's the my log book. I've got my backside distances, foresight distances. But notice here how I've got the heights of the instrument and the elevations already computed. That is no different. We don't do that any differently than we did before, okay? Everybody with me so far? Nothing's changed there. Now, here's what I'm gonna do. Okay, so remind me, what was the total length of the survey? Everybody remember what that was?
520.
520. So the total length of the survey is 520, okay? How far is it from our first benchmark to right here? Does anybody know that?
150.
150, because it's 75 and 75, right? Okay, so we'll say our first distance is 150, okay? So what I'm gonna do for this elevation is as follows, okay? So I've got my closure, my closure here is negative 0.06. So what I'm gonna do is I'm going to take this elevation, and here's what I'm going to do. I'm going to adjust it, okay? And what I'm going to do is I'm going to take 0.06 and I'm going to multiply it by a ratio. And that ratio is going to be the distance that I traveled divided by the entire distance for the entire survey, okay? And what happens is that elevation goes up a little bit. Why does it go up a little bit? Because when I started at 345.6 and ended 345.54, my elevations are a little too low. So I got to bring them all up just a little bit. With me so far? So this number should be a little higher than this one. Okay? With me so far? Okay. Now, this one right here. Okay? So the formula is going to be, okay, so I'm going to take 335.15 minus 0.6, and it's going to be something over 520. What do you think that number is going to be? Okay, 250. Now you said 250 because it's that plus that, right? But we've got to talk about the entire distance traveled from here to here. So it's not 250,
It's 400.
it's 400 because we've got to go from the very beginning all the way to where we are now. Because the very last adjustment needs to be 520 over 520. Does that make sense? So again, they all went up a little bit. This one went up this much. This one went up a little bit more, and this one went up even further. Because the idea is that the error compounds, right? If you have a little bit of error from this point to this point, then from this point to this point, you've got to account for that error that came from the very beginning, right? So the error has to, there's an additive nature to it. It's got to increase every little bit. Does that make sense? Okay, I want to take a step back and see if that part makes sense. Because don't worry, we're going to have an example where we do it together. So far, so good? Okay, let's do one. Okay, so let's look at a differential level example, and this is going to be a weighted distribution. Okay, so here's our field notes. Okay, now what I've got here is I've got a set of field notes. Now, just to be clear, this is the exact same example that we did last time. So if you go back to the notes, so this is the example that we did in class on Wednesday. These are the exact same measurements that we did last time. So like if you see here this height of instrument, this 105.51, 108.79, exact same data over here, nothing changed. The only difference is that I'm adding these backside distances and adding these foresight distances. So these heights of instruments and these elevations, same thing as we did before in class. With me so far? So what we're going to do is we're going to do a weighted adjustment or a weighted distribution of error. And so what I'm trying to do is I'm trying to do this the way that you would do it in the field so that the experience matches. So far so good? Now, I want to start with these backside distances. And I want to look at this one right here. Okay? Help me out. So I've got here the lower stadia and the upper stadia. So the lower wire was 5.11, the upper wire was 5.91. Okay? So what's the difference between them?
48.
Times 100? 80. Right. Yeah, so 80, okay? So I propose that this distance is 80 feet. Does that make sense? Okay, everybody with me on that? Now, before we move on, I want to talk about this other added value of this type of level, this 3-wire leveling. So I want to look at these numbers right here, and I kind of want to look at them over here, okay? So what this data is showing right here, what it's showing is that when you're out there in the field and you're eyepiecing this thing, you read this as 5.510. And you read this as what? 5.910. And what about this? Okay, so help me out. What is the distance here? What is that variation? What's that? 0.400, right? What about this one?
0.400.
Ah. So what I'm getting at is you're independently, so imagine yourself in the field. You're in the field, you've got the tripod set up, you're taking a reading, and you just look at each of these 3 wires, right? You're looking at an upper, a middle, a lower. And when you write that data down and take a look at that data, you should have the same difference here as you do here. If not, what does that mean? You read something wrong, right? So this method is forcing you to look at the data and go, wait a minute, do these make sense? You see my point? So there is another added benefit. So think about those benefits. Number one, the logic by which you adjust the errors make more sense. I mean, think about that. What we're doing in the field is we're saying if that shot was further away, we need to correct our error board. Does that make more sense now that you've done it? I mean, think about it. If you've got a shot that's 500 feet away versus one that's 20 feet away, you're probably more sure about that 20-foot shot than you are that 500-foot shot, right? So the distribution makes sense. You also get the distances that you need to classify the survey. That's your second benefit. What's your third benefit? You got to check on your readings. Does that make sense? That's why I like this method better. Because it's more involved. I will give you that. It's more involved. But you have a check on your readings. So far, so good? All right, so help me out. Let's get these. Let's get these and these. So somebody help me out. What goes in this second cell? So we go from 5.33 to 7.73. What goes right here?
250.
250?
2500, right?
What?
I can barely see it. 5.33, 5.330, right? And then
Yep.
7.730.
This looks like somebody who did not bring their Casio FX115 ES Plus or similar scientific calculator.
No, I just can't see
241
it.
Introduction to Geomatics. Do you have your Casio FX115 ES Plus or similar scientific calculator?
Heck yeah, that's what I look like. I just can't read it, that's the thing.
I know. And if there's any one disadvantage, sometimes the way you set the notes up, the numbers are tiny. So 5.33, 7.73.
240.
240. All right, we'll start getting some response from some other people in the class. Somebody else help me out. What do we got for this one right here?
2.5
Somebody not sitting in the back. 150. Okay, 150. Okay, 150. All right, this next one, what do we got? And again, look at the numbers, okay? So this central reading is 3.27, and we got 1.27 and 5.27. Those numbers make sense from a stadia standpoint, right? The difference between middle and lower is 2. The difference between upper and middle is 2, right? Those differences should be consistent, okay? Make sense? All right, so let's see if we can rapid fire down these. What do we got for that one?
120.
120. All right, what about the next one? Somebody else. Somebody over here.
160.
All right. All right. Somebody over here on the third one, somebody over here for the fourth one. Somebody over here. So it's 5.92 and 7.42.
150.
150. Okay. All right. Over here, last one. 6.39, 9.39.
300.
There we go. All right. Now we're making something happen. Okay. Does that make sense? Okay. So again, this is why I like this method a little better. Okay. Now, one thing I am going to help you out with, because we already did this before, okay? We're going to put a summation column down here at the bottom. And we already summed our backsides and foresides. Here we got 19.630. Here we got 28.310. Okay? Now, a couple things I'm going to check. Okay? So let's do our page check. So we'll do this right here. So if I sum up the back sides minus summing up the foresides, what do I get? 19.63 minus 28.310. What is that? Make sure we're all paying attention.
Negative 8.68.
Negative 8.680. Okay, what about elevation final minus elevation initial? So 91.23 minus 100. Did we get that right? Do we have a typo in here somewhere?
They're not the same.
Ah, I know what the problem is. This is supposed to be 320. See, it's like these page checks matter. This is why you do this. And notice how you don't erase. I see erasers in the field. No. Now what do we get?
I have a question about that whole erasing thing. I still don't understand, like, if you make like an obvious mistake, like if somebody got order 107.
Don't
right?
do that. You don't erase field notes.
But why? If it's obvious.
Because it's a legal document. You don't alter a legal document. Now what do we get? Is this 8.68?
Yeah.
Okay, all right. All right. Okay. With me so far? Okay, so let's write down some data over here. So C in this case is negative 8.680 feet. What about our distance traveled? What's the total amount of distance traveled for this entire survey? Say it again.
1,040.
1,040. Do I have a second on that? Somebody shaking their head no. How are we getting that? We're taking 80 plus 240 plus 150 plus 400. That, and that. Say it again?
1,600.
1,600. Do I have a second on that?
Second.
All right. Wait, hold on.
I'm in his brain now.
Okay, 1,600 feet. With me so far? Okay. Now the only other thing I want to point out is everybody in agreement that the elevations as a whole need to increase?
Yes.
Okay. So let's start off with this one right here, this 102.60. What goes into this cell right here? Okay. Well, I propose it's 102.260 plus. Okay, so what we're going to do is we're going to take our adjustment, 8.680. I'll adhere. But we need to multiply that times a fraction. Okay? Now I propose the bottom of that fraction is always 1,600. Okay? The numerator is however far we traveled from the very beginning to this point. And I propose that's 80 plus 120. Because that's how far we traveled from the very beginning to right here. So I'll even put a little number here. We'll say number 1, 2, 3, 4. And we'll say that number 1 is 102.260 plus 8.680 times 80 plus 120 over 1,600. So what do we get for that? We'll say 3 decimal places. Remember, these elevations need to go up. $103.35. Let's do 3 decimal places.
345.
Do I have a second on that?
Second.
Second. Okay. All right. So this second one. Okay. So what we're going to do is we're going to take our elevation. Okay. And we're going to add a correction. Okay. On the bottom goes our entire distance traveled, and on the top goes the entire distance from the beginning to our point in question, which in this case is 80 plus 120 plus 240 plus 160. You see that? And from the very beginning all the way to the distance in question. Because what we've got to do is this number has to be adjusted both for the previous error and the one on this turn, right? So we've got to add both this error and the new error. That's why we're adding everything. Okay? So this one's going to be
I got 101.545.
101.545. Do I have a second? Okay. All right. Let's check out our third one. Okay, so our third one. Can you all read this down here? Okay. So we'll take, all right, 95.940 plus, we throw a correction in there, times a fraction. The bottom is 1,600 still, and the top is 80 plus 120 plus 240 plus 160, and then we add our new terms, 150 and 150. So what do we get for that? I'll scroll down a little bit, make sure we can kind of read that.
100.823.
100.823. Do I have a second?
Yes.
So let me copy this down here so we have it for posterity. Okay, and so so first off, without doing any math, what should our last one be? 100. But let's just check, okay? So it should be 91.320 plus a correction. And again, 1600, 80 plus 120 plus 240 plus 160 plus 150 plus 150 plus 400 plus 300. And I'm doing this in a very formal, elongated fashion because as you get more comfortable with this, you won't need to do that. So, does this come out to 100?
Yes.
Yes. Okay. So, this is exactly 100. All right. Let's take a second, digest this. I want you to tell me what you think. Any questions? Does this make, this was the remaining question on the homework that we didn't cover. What is everything else between this and the rest of the homework? How are we feeling? Any questions? Everybody good? I do want to mention one quick field application of leveling, just to sort of like make the point of where a differential level could be applied beyond just basic, I guess, determination of elevations. And I kind of want to show you a simple example called a profile level. I'm not going to make you do this on homework or an exam or anything. This is just for your edification. A profile level is basically a more elongated application of differential leveling. And so let me give you an example. Okay, so I have here a parking lot. Okay, and I want to give you a somewhat real-world example. Let's say that the goal in this parking lot is to install a stormwater drain. Okay, so the idea is, so I've got a path that this stormwater drain is going to follow, and let's say the hydraulic engineer has determined that that's where the storm drain needs to be located. Okay, so what we've got here is we've got station 1 plus 0, 0, 1 plus 5, 0, 2 plus 0, 0, 2 plus 50, etc. Y'all know what I'm talking about now, right? There we go. See, we're getting somewhere. Okay, and what I've gone and done, this is data from a survey that I did, is I've got here this blue dashed line. This is existing elevations. Okay, so what I've got is I've got some notes. Here's some notes that you see here. I've got a benchmark site and did the back site, height of the instrument, and I've got a foresight done where I'm foresighting each of the points along this station. Okay, so this blue dashed line, this is the elevation. Okay, this is the elevation of the existing ground along that center line of those stations, right? And we collected a little bit more data around here because it was turning, right? So we said, let's collect, instead of stations every 50 feet, so you can see we got station here, station here, station here. When the storm drain was going to curve, we said, okay, let's collect a little more. With me so far? Okay, now this is where the ground is. What about the storm drain? Okay, so the storm drain's got to be a little bit below ground, and it's got to slope down, right? You can't have a pipe that's flat. It's got to slope down a little bit so that the water can drain, right? So the idea is we say, all right, this is the proposed elevation. And so what we do is we had in the project, what we did, we had a requirement that there had to be at least 4 feet of fill over the pipe of the storm drain. So by looking at the elevations, it was pretty clear that we needed to start that here, and we just made sure that as long as each of these we had 4 feet of cover, which we did. So we said, okay, let's look at this. So what we did is we said, okay, we wanted to determine volume of earthwork, but how did we do that? Okay, well, what we did is we took foresight readings along the station, but then we also took foresight readings on offset. So remember in lab 1 when we talked about offset, so if you had station 1 plus 0, 0, 30 left, or 1 plus 0, 0, 30 right, that it would be offset on either end. So in our field notes, what we've got is we've got this station and then 30 left, station 30 right. This station, station 30 left, station 30 right. This station, station 30 left, station 30 right, etc. And so what we can do is we can determine the elevation of not just the center line, but on 30 feet of either side. And then so what we did, let's say this is station 1 plus 0, 0. We got the existing ground. 30 foot over gives us this slope. 30 foot over gives us this slope. So this is actually from the CAD for the project. And so if you look at station 1 plus 0, 0, so let's look at these numbers right here. So this is station 1 plus 0, 0. This is 30 left. This is 30 right. So see how 30 left is a little higher and 30 left or 30 right's a little lower? So 30 left slopes up, 30 right slopes down. Drip down or come down on a 1 to 2 slope to where we get 4 feet here, 4 feet up, 4 feet up. We can compute our earthwork, compute our area on this station. Do the same thing for various stations along the section. The idea is to determine the total volume of earthwork that's to be, or the total volume of earth that's to be cut, the total amount of fill that's needed, etc. Right? And so this is an example of a differential level application, is a profile level, right? So the idea is that for each of these stations, we can determine the elevation and the offset elevation, and from that we could do excavation calculations, etc. It's a very simple setup because if you had line of sight for something like this, you could set up like right here, take a benchmark backside and just foresight everything in one shot. We couldn't do everything in this setup. We had to break a couple turning points because of the coverage and whatnot. But if you've got line of sight, you could do everything in one foresight, one setup. So you could go out there and collect all that data, depending upon how fast you were. You could collect all that data in a matter of 20, 30 minutes, go out and do your CAD work and your calculations and have the project done pretty easily. So it's a very simple but elegant application in the real world of a differential level. Any questions on that? I just want to give you sort of an aspect of where this could be applied in the real world. All right, any questions on homework or anything like that? I think I'm prepared to give you 10 minutes of your life back. I'm going to pull up the QR code in case anybody missed it for attendance. On Wednesday, your homework is due at 1 p.m. We are going to talk about homework exam. We're doing exam review on Wednesday. Be prepared for questions. I'll see you then.
He has risen. That's what you're saying. You know, out of all bad things